Hello community, let's go with this LLM on graphs, a brand new study by Massachusetts Institute of Technology, Cambridge and the Chinese University of Hong Kong. And we are talking about decoding on graphs. We have now advanced reasoning on knowledge graphs through a generation of well-formed chains within our LLMs. Now, this is nice because now we augment here our knowledge graph as a knowledge source for our LLMs when handling here question and answers task. And of course, we want to have here this additional knowledge here of our knowledge graph for the LLM reasoning. So we improve with the knowledge graph the parametric knowledge encoded in our LLMs. Now, you know, we have more or less two main directions how to do this. And here I have here this study here from end of May 2024, University of Minnesota, GNN RAG, Graph Neural Retrieval for Large Language Model Reasoning. And this is a beautiful study because it combines everything: graph neural network, LLMs, and the reasonability of graph neural networks in a retrieval augmented generation style. So we have RAG, we have LLM, and we have graphs. And we have also Decode available for you. Now, you know that they are talking now here about specialized, and it's a whole group, a specialized subgraph retrievers to retrieve here the question-focused subgraph from a complete knowledge graph, which are then fed into the LLMs for predicting the answer. Such approaches shift the burden of finding answers on our knowledge graph topology to the subgraph retrievers, while the LLM is here with its intelligence merely select the most possible answer from the highly concentrated subgraphs, and are not deeply involved in the graph reasoning process. And if you want to have a look here at the internal workings of GNN RAG, I think this is the study you should have a look for, because this is really a beautiful one. However, there's a second main direction that we take. Now, here we have Panasonic, Peking University, beginning of June 2024. Observation-driven agents for integrating LLMs and knowledge graph. And this is also a beautiful study, since we integrate now AI agents here, and we build a novel AI agent framework tailored for tasks involving here the parametric knowledge of knowledge graphs. So here we have a direct engagement of the LLMs in the reasoning process on the topology of knowledge graphs. So what we do, we have a series of operations on our knowledge graph topology, like neighbor entities exploration, path decision, you know, Dijkstra algorithm, our all-time beautiful one, until finally reaching an answer. So such approaches place a significant demand on the LLM's ability. So if you go with really small-sized LLM, less than 10 billion free trainable parameter, this can become, I don't know, a little bit tricky. So you better go for the huge LLMs here. If you want to have here a short explanation of our agent works, well, it is easy. You have your question, you have your task relevant entities, you have a knowledge graph, you build your triples. You remember we have a head entity, we have a tail entity, and we have all this relationship between them. Yes, and then you can sort them, you have similarities, you choose the top one, you have a refinement. And if you know this study, it's really a nice study. So, if you want to see here, if you want the pseudocode of this, beautiful. So for a knowledge graph-centric task, the observation incurs the problem of an explosive number of nodes, because if you have really complex knowledge graph, my goodness, you need a lot of graph computational power. So to address here the scalability challenges during the observation subgraph updating, they propose here a D-turn observation strategy where D represents the maximum hop depth. You know, if you have one node, you hop to the second node, then you hop to the third node, then you hop to the fourth node, and depending on how many hops you do, it grows exponentially. Beautiful. So now let's come to the new publication just 2 days ago for me recording this video here by MIT and Hong Kong. They have a brand new idea. Yes, if you just forgot it, this is the study we are talking about. And they say, hey, so we have now either these two main directions, and we see there's a tight coupling between the LLM stepwise reasoning capabilities, like in chain of sort or graph of sorts, and the knowledge graph. And they say this can be a promising solution to further advance the performance of knowledge graph question and answering. So therefore, they say we explore, let the LLMs reason directly on the knowledge graph topology. through a generation of reasoning steps. And the way we build this reasoning step, this is here the beauty in this study. So they say here, and this is a quote, and we propose DOG, decode on graphs, to make LLMs to generate well-formed chains on knowledge graph by enforcing here a graph-aware constrained decoding methodology and a beam search execution, leading to a better reasoning and answer. And now you might immediately see we have two topics we're going to talk about. What is their main idea? What is their main functionality? What is their method? We have two topics. Well-formed chains on a knowledge graph. I will explain this in detail. And then we have to talk in detail about graph-aware constrained decoding by our LLMs. So let's dive right into it. So at first, the concept well-formed chains. You know, chain of thought, chain of reasoning, whatever. So what we do now, we use these chains that we have on the knowledge graph topology to serve as a principle for making faithful and sound reasoning patterns here, reasoning chains on the knowledge graph topology. So let's start with a definition. A well-formed chain starting from query entities and leading to answer is composed of a sequence of interconnected triplets as reasoning steps, and each step of triplet can only grow from all previously visited triplets only. This has some quite restrictive implication, but let's talk about this a little bit later. So we have simply a chain, and we go here from a start entity, the query entity, and then we are looking here on our graph topology for the answer if it is encoded here in the graph topology. And you might say, however, wait a minute, under this, and this is the beauty, the training-free setting. We do not have to have a fine-tuning of our knowledge, of our LLMs with the data of our knowledge graph, but this is a training-free setting, which will bring us some problems, but more about this in 2 minutes. So it is almost impossible to ensure the generation of such beautiful chains simply by some conventional techniques like ICL, like our in-context learning, or prompt engineering, due to the obscure structural information after we have done the linearization of all the graph entities in the input prompt to our LLM. Plus, difficulties in interjection of the concept into LLMs. We have some limitation with some ordering problems and. But never mind. So they say, hey, so we further propose now a second idea to solve this problem. This is now a graph-aware constrained decoding. And by restricting the scope of the valid tokens as an output, this hard constraining is able to strictly regularize the LLM's generation to be a well-formed chain. So what we do, we have a regularization process of our LLM, as we always have in our transformer architecture, but now here by valid tokens that are defined here on the knowledge graph, and then generate here a well-formed chain. And you remember, the well-formed chain has some restriction of itself, because each step of the triplet can only grow from all previously visited triplets. So this is quite strong here. So let me give you a simple example, because an example is always beautiful. Now we have the theory. Now you understand it immediately. This is from the original MIT Hong Kong publication. So let's start. We have here our system prompt. Hey, your helpful assistant can analyze the knowledge graph, and yes, you know it. And then we do something in context learning. MIT. They say, hey, we give you 3 examples. We show you exactly what we want. And then I give you here the question and the graph, and I want that you answer. Give me here our 3, 4, 5, 10, 100 in-context examples. And what they do here in this in-context example, I will show you in a minute, they do here a linearization of a graph structure, which is an interesting structure in itself, given that we have here the graph also. But if we have this, we start now with a query-centric subgraph, step 1. And let's say we have a concrete question. And here the question is, what is the national flower of the location where the movie Blue Hawaii is set? So what we do, we have to construct triplets. So you know exactly how we're going to start. So we say, okay, our first node is, for example, Blue Hawaii, because this is the name of the movie. So what we are looking for is now what does the knowledge graph has encoded in each knowledge graph representation. So we follow here simply all the edges, leaving here our primary node Blue Hawaii. And we see we have here an edge with the entity film, feature, film locations, and the next node here is Hawaii. And you say, what an amazing idea. And then we have also here an edge that go here film, performance, the actor, and this is Tiki Hanalei. So you get immediately an idea how we build our query centric, because we start here with Blue Hawaii from the query subgraph. Now the next step is quite interesting, a trie construction. And I will show you this in a minute. So they simply go, okay, so we have here the beginning of a string, Blue Hawaii, and then we found here film, featured, film location, answer is Hawaii, and we have the end of string. So we built this, whatever we have in our knowledge graph. And having this, now we have more or less the answer, yeah? Because we have Blue Hawaii, then this is our first node. Then we have here, if you want, the edge quantification. And then we have Hawaii as our second node. And now we do here a query-centric subgraph, the step 2, and we look at all the possible links that we have. And now we take Hawaii, for example, here as the starting point, and we do the same as we did here. Then we look at all the edges that we have, and we look here all on the edge. We have here some attributes here, for example, location contained by, or symbol of administrative division, my goodness. So whatever you have in your knowledge graph, you just go step by step, and you always use here the one that is available in the knowledge graph. And then if you do all this, you run all these possibilities, you get your final answer. Great. Now I have to tell you, I did not know what a trie data structure was exactly. So here for my green grasshoppers, because I also had to learn this, this is a trie, also known as a prefix tree structure. It's a tree-like data structure that stores here a dynamic set of strings where each key, or usually words or sequences of characters, like we have here. So each node in a trie represents a common prefix of some keys, and the edges represent the extension of the prefix by one character or more. And tries are now a beautiful data structure efficient for tasks where we have here prefix search and autocompletion. And this is exactly what we are looking for. So let's go with a trie data structure. So the key properties of a trie, you have an empty root node. We have our edges that are labeled here with some tokens. And we have our nodes like Hawaii. And we have then the end node, the child node, or the leaf node, indicate here the end of a valid key of a word or a sequence. And if we use now the tries in a graph-aware constraint decoding, something beautiful is gonna happen. We have another constraint imposed on our system. So in the context of graph-aware constraint decoding for LLMs working with knowledge graph, a trie is used here to dynamically constrain the output tokens that the LLM can generate at each step, thereby ensuring that the generated sequence corresponds to valid path in the knowledge graph. And now you see what happens. We extremely limit the complex search space that we normally have. And we say, hey, listen, you're only allowed here to discover paths that are encoded in the representation of our knowledge graph. And only those paths are valid paths for you to build as an LLM your token construct in your reasoning process, in your causal reasoning, for example. And of course, if you just do not want to go when you get here some paths back with the best one, you want to have here multiple valid reasoning path. So think about here, the best path has here a probability of 100%, but the 3 closest paths to this optimal path, they have a probability of 99.5%. So you also want to take here those very closely located paths also. So you go with multiple valid reasoning path, and thereby you use a beam search and the beam width. It's like if you have a beam of light, if you make this cone of the light a little bit bigger, then you can see a little bit more of the surrounding, and you do not just have an absolute focus only on a point source. Great. Yeah, highest confidence scores, great. So what they said now for MIT and Hong Kong, for their particular implementation, we further integrate here the decoding on graph with a triplet level beam search execution. And now they make it even more interesting because they realize they more or less have 2 steps to go. No? They have here a token level beam search, because the token levels can also have real close by alternative tokens, and they go for a triplet level beam search. Let's see this in an implementation. And I was looking forward how they code this, how they implement this. And here we have now the prompt from MIT and Hong Kong for decoding on graphs on a knowledge graph question and answer session. By the way, if you go to the original publication, this is table 6. And so you see, you say, hey, you are a helpful assistant, you know all of this, this is here in the system prompt. Answer should be given on grounded reasoning change and think step by step, CO2. Reasoning change should be logically complete, but have as few steps as possible. And then now we give here an in-context learning example, example 1. Now you know that we want here to augment our parametric knowledge of the LLM with the knowledge graph encoded knowledge. So what we have to do, we have to give, since we are operating here in a text, the linearist knowledge graph transformation of all the node and the edges now to our LLM. Because the LLM needs here a linear string of tokens. So they chosen here, for example, this example, Bahamas, location, country, first level division, Grand K, okay. Next one, Grand Bahama, location contained by Bahamas, Bahamas, location contained by Grand. So whatever is here a valid link in our knowledge graph, whatever nodes we have available in the knowledge graph, we have now a linearization that our LLM is able to understand this. Might not be the most intelligent way to represent this, but okay, the authors have chosen this here for the input to our LLM, and this is just example 1. They have chosen 3 in context ICL examples, so imagine 2 and 3 examples given in addition. The authors tell us, hey, we transform now the whole graph that we have into a linearized form to accommodate text form input for our LLM. Now, this is something we could discuss. Is this the most intelligent thing you should do if you have an encoding and a graph structure to go now and break it down into a linearized form? But anyway, we go with MIT. Because, you know, I have this example just in one of my last videos. I have here a linearized form, you know. I have here some rules, some very simple rules, you know. Just if A and B, then C. It's simple. It can't be simpler. Graph, you have exactly. You have a triplet, A, B, C. And then I just have facts. This is also in a linearized form. There's a linear sequence of sentences. And then if you look at the logic test, you see that even the latest Claude 3.5 Sonnet, the version 2, just coming out 3-4 days out. It fails several times on a simple logic test. So this linearized form as an input to an LLM, Sonnet version 2 would fail here in the logical reasoning because it can't handle this complexity. If you want, have a look here at my video. I show you this in detail. Coming back to MIT and Hong Kong. So they say here, we have this powerful graph-aware constrained decoding here in our decode on graph. And these mechanisms ensure that the LLM used here in this decoding generates reasoning steps that are now logically, quotation mark, sound and grounded here in the provided knowledge graph. Now you know that a knowledge graph is never complete. So here you have a strong limitation. Hey, your knowledge graph is better perfect, otherwise you miss out here on different connections. I tried for my green grasshoppers here. I took here each single word or sequence here, so graph-aware, constrained and decoding. So this graph-aware, this decoding process is directly informed by the structure or by the topology of the knowledge graph. Constrained, as I told you, is restricted to a specific set of possibilities. The constraints are dynamically updated based on the current state of the reasoning process and a specific knowledge graph topology, and decoding is simply here the process of generating text from the LLM by the LLM. So, okay, we say good for this particular idea, methodology, great. And I ask here my GPT-4, give me an example here of this knowledge graph structure here with these query-centric subgraphs that have this limitation here. So easy, let's start here a question. What is the national flower of the location where the movie Blue Hawaii is set? And the knowledge graph contains here entities and relations relevant to Blue Hawaii, Hawaii, and Hawaiian hibiscus. You get the idea where I took the example. So step one, initialize the query-centric subgraph. So what we have, we build triplets from our unstructured data, from our text, from our English text. And the triplets are simply Blue Hawaii, film, feature, film location, Hawaii. Blue Hawaii, performance actor, Tiki Hanalei. And we build here all the triplets out. Great. Then the authors, if you go according to MIT in Hong Kong, we build now a trie, a specific tree structure. Nodes represent the tokens, the words or the subwords, the edges connect the tokens to form a valid sequence, so our triplets, and the path from the root to the leaves represent all possible valid triplets starting from the query entity. And then we build here head and relation and the tail element of our triplet. Yes, you get the idea. And then when the LLM starts generating the first triplet in the reasoning chain now, it is constrained to, and now this is important, so the first token must be the Blue Hawaii, since it's the query entity. This is where we start. The second token can be any relation connected to our starting node, Blue Hawaii, in the trie. Valid options, for example, might be where we have a link going out here of Blue Hawaii is film locations or performance actor, like we just had here in these examples. And the third token must be the tail entity connected via the chosen relations. So for the LLM, if we choose here the edge feature film location, then the only valid next token is given by the knowledge graph topology, and this is the node Hawaii. So you see, this decoding on graph is a rather simple methodology. Dynamic token validation, yes, and everything. But I just want to show you, sometimes this scientific paper looks a little bit complex, but if you think about it, the base idea is rather simple, no? So it's always good to have an example. Key benefits, the author tells us, hey, if we do this, it prevents our system to generate hallucination, like a LLM working on its own would do. It narrows here very effectively the search space. Yes, of course, we only allow connection that we have in our knowledge graph. No, not in the knowledge graph embedding, but in the knowledge graph topology. And then, yeah, sound reasoning, same limitations. So they say, in essence, a graph-aware constraint decoding here, this is a crucial technique in our decoding graph that transforms the LLM's free-form generation of maybe causal reasoning token sequences into a structured reasoning process guided only by the knowledge encoded in the knowledge graph, and only what is encoded in the knowledge graph is a valid path, which is a massive limitation given the knowledge graph may be incomplete. And you already get it. Now, if you are a subscriber of my channel, you know what's going to happen now. Because I looked at this again, at the definition of the well-formed chain, and then I looked here at the query-centric subgraphs and those triplets on the query-centric subgraph, and I said, there is a strange feeling, there is something. And then I said, hey, wait a minute, this cannot be true, or? And then you and me, we both remember that on the beginning of October 2024, I went with you and I presented you this study by Harvard University and Pfizer on a knowledge graph-based agent for complex knowledge-intensive question answering in medicine. This was Harvard Med School. And if you don't know, if you are not a subscriber to my channel, well, this is the video you should watch. Harvard presents a new knowledge graph agent for a Meta AI system. And in this video, we talked about here a real beautiful complex structure to generate, to review, to revise, and to answer exactly more or less the same topic we just found in the MIT study. However, this Harvard study, if you remember, we were working here with embeddings. We had self-learning. We had that the knowledge graph was also not an absolute object, but given the parametric knowledge of our LLM, we could inject new nodes and new edges, new connection in the knowledge graph. We could build up the knowledge graph with the parametric knowledge of the LLM and come here to a self-learning, self-optimizing system. So here we have it. We have here from October 7th, 2024, Harvard and Pfizer, with this video and this beautiful, real beautiful paper. And then today, October 24, so 2 and a little bit weeks later, we have this publication by Massachusetts Institute of Technology and Chinese University of Hong Kong, almost on the same topic. So I went back and I read the study and I had again a look here at this publication and I said, what happened here? Now let me formulate it in a friendly way. If you are new to the topic, I would here highly recommend you start with this very easy and simple introduction for an LLM operating here on a knowledge graph. Here the latest publication just 2 days ago by MIT and Chinese University of Hong Kong, they give you a beautiful introduction, a simple introduction to LLM operating on a graph topology and using here the encoded knowledge of graph structure to enhance the causal reasoning of our LLMs. And if you say, hey, that is so easy, then you can go to a really beautiful scientific study by Harvard Med. They go extra 400%. They do an embedding, they have a LLM and a knowledge graph that can improve each other. You have beautiful methodologies from embedding, building here aligned embeddings in complete new vector spaces and doing here some beautiful operation. So let me formulate this. The study that came out weeks later is now here our introduction study that I would formulate it here. And then if you want to go for the real thing, if you want to say, hey, give me all that you have here on knowledge graph and agent, AI agent, LLM for complex reasoning, for complex knowledge intensive question and answer in the medical domain, then I would say go with Harvard. Because, to be honest, in this particular topic, Harvard Med is really impressive with its implementation of a medical LLM and a knowledge graph. And I have to tell you, MIT is a very nice and very easy and very simple, a very scaled down implementation. So there you have it. If you want to go and you say, hey, I have knowledge graph in my domain, in medicine, wherever you are, in theoretical physics, or maybe in finance, or I don't know what your domain is, take care of this encoded knowledge in our knowledge graph. This is a beautiful help for the causal reasoning that is going on here in our LLM, and it can increase the performance of LLM significantly. Okay, I hope this was a little bit of fun. I hope there were some new ideas for you, and it would be great to see you in my next video.